If we achieve this, the next step in density to cover this 20,000 or this 10,000 gap that we talked about would be to increase the current to full power. At full power, we expect to go from our present 1.5 megaamps to almost 3 megaamps. And that will increase the density tenfold. We get a 20-fold benefit in density simply from having the heavier elements. The process works out in such a way, and this was theoretically predicted in my work back in the 80s, that the heavier elements have a greater compression ratio. So for the same starting density, we get about 20 times bigger finished density. So if you put those numbers together, that's how, over the course of a year to 18 months, we expect to close that 10,000 density gap. It sounds like a lot, but in physics experiments, it's not unusual to get these big jumps. At the same time, by compressing the field more and more, by the self-compression of the plasma, we expect to get up to the magnetic field that's necessary for this quantum effect to prevent the X-ray cooling. So with the filaments, we expect to go from our present 0.08 gigagauss to about 0.6 gigagauss. With full current, we'll about double that, and with the greater compression with hydrogen-boron, PB11, we'll get up to about 10 gigagauss, which is well beyond what we need. Now, that's not the end of the story, because the tungsten electrodes are extremely tough for everything that the machine produces except X-rays. As we get closer and closer to net energy production, the X-rays are going to go up until thousands of joules are being emitted as X-rays. And the unfortunate part is that tungsten, as a heavy metal, is very good at absorbing X-rays. So the X-rays will be absorbed in a very thin layer of tungsten, and that means that the tungsten would start to crack. So we need to replace that with beryllium. Beryllium is the lightest metal. It only has 4 charges, and most of the X-rays would pass through it, and the ones that don't will be spread out. Problem with beryllium is cost. At the moment, the United States government has established, I'm not sure how, a worldwide monopoly on beryllium, and they gave that monopoly to a single company, and we have to buy from that company. Oddly enough, beryllium is quite expensive. So our estimate is, or their estimate is, that the one-off single unit production cost of these beryllium electrodes would be something in the area of 200 to 250,000. Since our budget is only about $500,000 a year, that puts a real dent in it. That's what we're crowdfunding for, is that boost in our budget. Now, people ask, well, if we got to break even, what would be the engineering challenges to go beyond that to get to an actual generator? Now, we have a very small staff. I'll get into that again in a moment. So we don't have time to look in depth at the engineering challenges, but we do know what they are. First of all, even with these electrodes, there's a certain minimum amount of erosion that's unavoidable. It's a process called sputtering, which is when the ions smack into the electrode. On occasion, not very often, one of the atoms of the electrode gets bounced off. So there's a physical erosion. Now, that might let the electrode last a few weeks before its shape is significantly distorted. And that might be enough. That probably will be enough, because if we change out the electrodes every few weeks, and we have to shut down the machine for maybe half a day, that's still more than a 90% availability. And that's pretty good compared with our existing energy sources. Second, the anode is going to be heavily heated by X-rays. So that's going to be an upper limit in how fast this machine can fire, because you have to take all of that heat by some coolant, probably compressed helium, out of this very small anode. And we have to worry that the boron is going to simply precipitate out of this very hot gas, because boron is at room temperature solid. So we can't fire it too slowly either. So that's why about 200 times a second is going to be about right. So these are some of the engineering challenges that we're going to have to deal with in the engineering phase, which would take a much bigger staff. The final question I've been asked and I want to deal with before we open it up to questions: why has it taken so long? I mentioned that people have been working on the dense plasma focus for about 40 years. Why aren't we already there if it's such a good machine, it's so cheap? The first, second, and third reasons are money. Even though this machine is very inexpensive, and we built our device for about $500,000, it's totally underfunded. Underfunding has many malignant effects. First of all, you pick your materials on the basis of cost. Somebody asked me, well, why didn't people go to tungsten? Are you the first to discover tungsten was better? No. This was published 20 years ago in the literature that tungsten was vastly superior to copper. Tungsten is about 10 times more costly than copper. Copper is a very cheap industrial material. So that's why people stayed with copper. They just didn't have the budget to even contemplate going to tungsten and looking at why it would be better. Second of all, there are too few large experiments because of funding. Our device is approximately the third most powerful device in the world. The biggest one is in Warsaw, and the second biggest one is in Las Vegas. And if you have very limited funding, you make a single big machine and then you're sort of stuck. The one in Warsaw is about 30 years old. And when people started to notice this impurity problem, many of them went in the wrong direction. They wanted to spread the current out by simply making the device larger. The problem with making the device larger, as we pointed out theoretically, is that the magnetic field, the density all goes down. So your yield is adversely affected. Also, if you've got a large machine, your expenses go up in terms of material. What to us, the tungsten electrodes cost $60,000, to our colleagues in Warsaw, the same electrodes would cost $500,000. And finally, you have enormous understaffing. Most experiments have only a few, 2 or 3 physicists working on them. Warsaw is an exception, they have a dozen. Our staff is extremely tiny. I and Ivy are the full-time staff. Ivy does everything else that is not directly connected with the lab, the website, the computer work. We have Fred Van Russell, who is part-time with us as an electrical engineer. We have Warwick, who was working full-time as a contractor on our simulation. And we're going to have, and we have Bob Fitzgerald, who's out there raising money for us. And in the lab, we're going to have a new person, Tony Ellis, coming on board. That's a ridiculously small staff, even for a device as small as the plasma focus. We could easily have 5 physicists working productively on this. This is all money limited. And 5 physicists don't work just 5 times faster than 1 physicist. We come up with good ideas by talking to each other. So the key problem with this entire plasma focus field has been enormous underfunding, which comes back to the crowdfunding, which I'll end on. We don't expect crowdfunding to substitute for the government funding that really has to be going into devices like the plasma focus and the many other good ideas people have come up with to get to fusion that are other than the giant tokamaks. But crowdfunding can act as a spark, because if we can use crowdfunding to get the money we need for vital parts to get to net energy out, then I think government funding will flow. People will say, these other alternatives are really working. When you look back at what I started with the consequences of getting something that is not just clean, but is cheaper than all other energy sources. I want to emphasize that, because as far as I know, no other alternative energy source, except ours, would be many times cheaper than existing energy sources. Then you get rid of the other energy sources. You wipe out oil and gas and coal and all the pollution that they create. You wipe out nuclear fission. They simply become obsolete. Given the enormous impact that this has, it's crazy not to put money into it. This is a research program, so can we guarantee success? No. If we could, it wouldn't be research. But this, we know of nothing, and no physicist has pointed out to us anything that prevents this approach from working. Given the consequences, it seems to me very logical that people should chip in. And if they do, and this is the slogan of our campaign, we will give power to the entire world. As we put it, let's focus fusion, empower the world. Thank you very much for your attention, and we'll be open for questions.
A slide I'm not sure you showed, the amount of energy, fusion, heat energy you get out is relatively modest, I think, compared to the amount of electrical energy you put in. Now, that means that you're dependent on turning all of the heat from the electrical input pulse plus the fusion back into electricity with an extremely high efficiency in order to get any net useful output at all. Higher efficiency than the less than 50%, but the best steam generated. Now, that does, what efficiency, can you remind us, do you need from that? And how much would the efficiency have to drop for the whole thing to become unviable? Because it's quite a small margin there, isn't it?
Well, you're absolutely right. We need high efficiency, but we can get high efficiency from direct conversion. With a normal steam cycle, there are thermodynamic limits on how efficient they can get, which is about, as you said, 50%. This device doesn't have that limit. The conversion of ion beams to electrical energy is based on the same technology by which we produce microwaves for our communication, which is converting an electron beam into energy. It's a very mature technology. There's been research published that show efficiencies of over 80%. And there's been unpublished research, which has been claimed on the web, of as much as 87%. So that's very highly efficient. In the case of the X-ray device, this is our own patented invention, so it hasn't been tested. But it's fairly straightforward to calculate the efficiency, and we calculate that efficiency also at about 80%. Now, the one thing to understand is this is 80% of all the energy. It's the input energy and the X-ray energy. There's very little energy dissipated within the machine. There's some loss to electrical resistance, but it's pretty low. So we've added up, we have a diagram, a Sankey diagram on the website that I don't have in this presentation, that shows all of the potential losses. And when you get all of those potential losses, you get back down to an overall thermodynamic efficiency of about 50%. So about 50% of the fusion energy will be turned into net electrical energy, and about 50% will have to be dissipated as heat. So even though we're producing only about double the energy that comes in, the key question is, do we get net energy out? And the answer is yes. Now, how low do these efficiencies have to go? Probably, we could make do with something like 70%. And 70% with this ion technology is really well below what has already been achieved. So the key thing is demonstrating the net energy in the lab, that we can get at least double the energy out that we put in, because we're going to be capturing both that input energy and the fusion output. Does that more or less answer?
Yes, yeah, but as you say, it's quite interesting, yeah.
Okay. Yes.
So when you get beryllium fusion, you get alpha flows out. They're born isotropically, I assume. So how do you end up with a nice beam?
Right. This is boron. I think you misspoke.
Oh, yeah. Yes.
Boron is the fuel. What is it? This has been researched extensively. Many groups have seen these beams. So as I said, the third step is the formation of this plasmoid. Well, I don't think we can capture that directly from the... Well, yeah, let me go back to it. I forget where my plasmoid is. That's this. There it is. Boron. We have trouble finding things in the lab too. So this plasmoid is born, and you remember the whole thing about the electrons circling around the field lines. Well, by Maxwell's equation, an electron that circles, that's accelerated, is emitting radiation. That's called synchrotron radiation. However, the synchrotron radiation doesn't have enough frequency to get out of the plasmoid. It's trapped. As the plasmoid becomes denser and denser, and the field is concentrated at the center, the frequency of that radiation gets higher and higher, until at the very center, the frequency is high enough to suddenly escape. So what happens is, and as I say, this has been demonstrated in many experiments, you have a sudden escape of energy, a very small time scale, hundreds of picoseconds. And that means that there's a sudden drop in the magnetic field. Well, again, according to Mr. Maxwell, if you have a sudden drop in the magnetic field, you get a tremendous electric field. So this electric field accelerates electrons in one direction and ions in the other. So that's why the energy comes out in a beam. Now the electron beam at the moment just crashes into the anode. We've calculated at higher densities, it will dump most of its energy into the plasmoid to accelerate its heating, and just a trickle will come out. Same number of electrons, but at lower energy. The ion beam, because of the heavy mass of the ions, comes straight out, deposits very little energy within the plasmoid. And the magnetic field of the ion beam actually concentrates it into a narrow beam. And if you want to see this on a dramatically larger scale, you get this. This is a beam from what's called a Herbig-Haro object, which is basically any star in formation goes through the Herbig-Haro phase, and it emits a very nicely collimated beam. Now, my actual theoretical studies of the dense plasma focus started out by modeling these beams from quasars and Herbig-Haro objects as the same physical process or related physical process to that occurring in the plasma wave. And we've measured these beams very carefully, and many other groups have, so we know that they exist and at high current. At low current, they're collimated, they're basically a cone of about 6 degrees. But at high current, they become collimated into something like that, which is basically a collimated beam. Yes?
And you mentioned that the dense plasma focus is invented at the same time as the tokamak, so how can the tokamak become a mainstream fusion machine?
Yes, that's an interesting tale, but it's more a tale of sociology than physics. I mean, what happened was that in the 1970s, and some people here might remember, but most of you will have to remember from your history books. In the 1970s, there was an enormous increase in the price of oil. And the price of oil became a very highly charged political issue, including in the United States. And Congress felt that they would get political, congressmen started to feel that they would get political gain by saying, we're going to put money into the solution and making America energy independent. And this was similar in many of the developed countries. At that time, fusion research really did not have a clue what would be the best device. But there was progress being made with the tokamak, which was a relatively young device. What was unwisely done, very unwisely, is that the bureaucrats in charge of the program and some of the physicists went to Congress and said, we have a solution. It's the tokamak. We know how this machine works, we just have to scale it up. It's an engineering problem, just like the moonshot, which had just been completed. This wasn't true. People knew it wasn't true. It wasn't an engineering problem, it was a science problem. It was scientific research. People didn't know what the best truth was. But having made this Faustian deal, everybody got sunk deeper into it. Because as the problems, the scientific problems of the tokamak, which is basically these instabilities, they're filled with filaments, but they're very undesirable in a tokamak. Basically, they got pushed back, the deadlines got pushed back further and further. Congress started to apply more pressure to say, well, you have to make these deadlines, and since you're not making your deadlines, we're cutting your funding. So the response of the bureaucracy was, well, we're going to concentrate more and more on the tokamak, and we're going to save money by throwing out all these other alternatives. So